Hello everyone. We will be starting with the system Verilog for functional verification training. Um, Let me give you a course overview. This part of the training, system Verilog for functional verification part of the training, will go for around 6 to 7 weeks. 7 weeks on the upper side. We will have theory sessions and lab sessions. We will inform the schedule in the group, and for the people who are attending from the happiest minds, the timings have already been informed to you in your respective groups, and we'll be doing the training as per that schedule. uh, okay, let me get into the presentation. So this will give you an idea of what to expect in the training and what are the prerequisites. Okay, just before that, about myself, my name is Srinivas. I'm the founder of the institute. I handle the front-end and functional verification activities at the institute. Okay, so let's start off with understanding the course prerequisites. One of the prerequisites is you should be familiar with Verilog from a design and verification perspective. You should be familiar with basic concepts like what is a task, what is a function in Verilog, and given a simple example, let's say if I ask you to implement, let's do an activity, everyone. That will be good to start off to understand your comfort level with Verilog. I want you to implement a function by name sum. Inputs, it takes inputs as a comma b. These are integers, and output is a return argument, return of the function. Can you please implement this function in Verilog? Please implement this function in Verilog. I want everyone to work on this and post the answer in the chat window. I'm just trying to get your comfort level with Verilog, because some of you have, I mean, the students of VLSI group, you have completed Verilog, but even then I want to know, are you comfortable with the basic concepts of Verilog? Because in case you are not able to do this, I will be asking like this another series of 2 to 3 questions. That would give me an idea about what is your comfort level with Verilog. Only if you are able to do these kind of things, you would be able to cope up with this 7 weeks of training, because we are going to do a lot of things in this 7 weeks time. Almost close to 600 slides of presentation. So you might imagine what is the depth to which this training will go. So for you to be able to learn this, you should be familiar with very basics of Verilog. So I have given the requirements. I want everyone to work on it and post the answer in the chat window. Please do let me know if you have any questions. I will be counting the responses, because no need to code module, Sudipta Ranjan, because I asked only the function. So just implement the function, that would be sufficient for me. And anytime I make the names, note of names and anything, don't take offensively. I'm just trying to make the session interactive. I want everyone to participate in the session. That is the primary thing. I mean, if you read one of my slides, I would say that the expectation from the students would be you should complete assignments as per schedule, and you should be proactive in the sessions. What is meant by proactive is always respond during the sessions and make the sessions interactive. That makes the overall course very interesting for you as well, right? Yeah, now please continue, because I don't want to be just speaking. I have told that these are integers. Inputs are integers. Okay, thank you everyone for participating and posting your answers. So let's just see quickly how to do that. While I'm doing, you can correlate with whatever answer you have posted and see where you have done wrong. In case you have done correct, that's very good. But otherwise, if you have gone wrong, please correlate where you have gone wrong. So first of all, we are implementing a function. The return type is integer, and the name of the function is sum, and it has got two inputs which are integers. So since they are integers, so I have to declare input integer A, input integer B. And in Verilog, everything has to be between begin and end. These are the basic guidelines. Now, how do we do that? Sum equal to A plus B. So the few things you need to remember is, I mean, in case you already got used to system Verilog, then you might have written return A plus B. That is not correct in Verilog. Even if you have done, that's fine, because then I would assume that you are comfortable with little bit of system Verilog also. So you can correlate. So first thing is int is not there. You always have to write integer, and begin end should be written, and integer should be declared as a return type. So these are the few things you need to remember. Now let's do one more simple question. Now let's say assume that there are two arrays, two integer arrays, integer int a1 of 5 down to 0, int a2 of 5 down to 0, and int a3 of 5 down to 0. So what I want you to do is write a for loop to call above function, above some function, whatever some function we defined, to add elements of int a1 and int a2 and keep them to put put the output into int a3. So this would be the last question. Okay, I won't be keeping it without starting the theory. I won't be just keeping the questions only. I'm just trying to get your comfort level with Verilog programming, so that I know where to, at what stage to start off my training with. So you can please work on this, everyone. Please don't declare again. See, do not declare again. I just directly want you to start off writing for loop. And what you can do is you can open a GVim window, and there you can start developing it. Whichever, instead of GVim, let's say you are already comfortable with some other text editor, you can use that. In case you are not really comfortable with any text editors, I'll be providing you an GVim usage video. Please go through that. That will help you learn the shortcuts. What I mean by shortcuts is how do you delete, how do you copy, how do you paste it, those kind of shortcuts in GVim you can learn through that video. That will make your overall programming expertise uh, very good. Okay, so I'll be sharing that video. Please go through that. And I think for the students who are already from Verilog training of our course, they would be already comfortable with this. And please note that I'm not trying to judge, and I'm not taking any feedback from your responses. It is just to make sure that, just to get a comfort feel. Okay, even if you code it right, wrong, it doesn't really matter. At least as far as assessment is concerned. So I got one response. Tamal and others, Chetan, what I told is call above some function. What is the intention of this question is how to use a function, how to use already implemented function. See, already we have implemented a function sum. Just want to know how will you call that sum function to do this addition. See, already we are doing the addition, so I don't want you to implement the plus operator. That is what you have done. I think some of you have done. So I got around 5 responses so far. Okay, fine. Thank you everyone for posting your answers. So let's see this now, how to do for I equal to 0. Now since we are using I, we should declare integer I less than or I less than 5, I equal to I plus 1, begin end. So int a3 of I is equal to sum of int a1 of I, int a2 of I. So this is what I was expecting you to code. So we already have a function by name sum, which takes input a and b, which are integers. So I'm passing one integer by taking the index. I'm passing another index. Output is being assigned to int a3 of I. So you might have noticed that I'm focusing on the basic comfort level with task and functions, and I'm also focusing on your comfort level with how to use a function and how to work with arrays. You will notice that going forward these things form a very important aspect of any programming language. I mean, even if you go to C++ or even Verilog system Verilog, task and functions and arrays are very important aspects. So that is one of the course prerequisites. Basically, you should be good with task functions, how to work with arrays, how to work with vectors, the basic concepts of module coding. How do you declare inputs, how do you declare outputs, how to declare reg and net, and then how to do test bench coding. And basically you should understand the intention of test bench coding. See, when I say test bench coding, I am not expecting you to be good with system Verilog here. Okay, why are we developing test bench? Okay, can someone tell me what is the few reasons why we develop test bench? I mean, what is the intention of test bench development?
To check the design is correctly working or not, giving the random inputs.
Okay, yeah, anyone else can?
Yes, sir. Assigning the variables to the inputs and getting the outputs to check whether our design is working properly or not.
Yeah, anyone else? I mean, see, even if, when I say anyone else, so yes, basically to check the function design behavior. Okay, so to check the design behavior matching as per the specification. I mean, is it matching the whatever has been provided as per the part of the specification is what we do. What do we do in test bench? Two things we do. One is generate the scenario, generate the stimulus or scenario or inputs, whatever you call it as, same, and drive those inputs to the design. Second is collect the outputs and compare them against expected values. Okay, why am I writing these notes is, I mean, you should be comfortable with these terms. Where, I mean, in Verilog, you should understand what is meant by generating a stimulus. Typically, how do you generate stimulus? What is the one very important Verilog construct we use to generate stimulus? Can someone tell me?
Dollar random.
Verilog, dollar random we use, right? Dollar random or dollar random, urandom range.
Q random.
Various things are there, 2-3 things are there. That is something we frequently use in Verilog to generate the stimulus and drive those inputs to the design. So when we say driving inputs to the design, what do we mean by drive inputs to the design? What does it mean?
Mapping the test bench variables to the input using the instantiating the design DUT.
Basically driving the ports of the design of the DUT with the values, with the input values. Correct, right? So what this much understanding you should have. What do you mean by generating the stimulus? What do we mean by driving those inputs to the design? What is meant by port connection? How do we instantiate DUT and how we drive inputs to the DUT? That much comfort you should have. Then coming to the second aspect, that is the checking whether the design is working properly or not. For that, you should be comfortable with what is meant by collecting the outputs. Collecting output is nothing but sampling the output values at positive edge of the clock, depending upon whether it's combinational or sequential. You get the outputs, compare those outputs against the expected output values. So this level of comfort you should have. So what do I mean here? If I give you an example of a 2x1 multiplexer, you should be comfortably able to develop a test bench using Verilog. All the aspects, instantiation of the multiplexer, applying the inputs, using dollar monitor to display the things, all that comfort should be there, so that you primarily understand the test bench development. And this intention of test bench development doesn't change when we go from Verilog to system Verilog and system Verilog to UVM. This intention remains same. So this intention of test bench development is same in every language. Whether you use Verilog, whether we use system Verilog, whether we use UVM, our intention is same, and the way we do that is also same, more or less same. It is just that what we want to do is same. Only what differs is system Verilog provides more constructs, so which makes generating the stimulus lot easier. That is, generating the scenario and generating inputs becomes a lot easier, which is difficult in Verilog because of limited language constructs. And driving those inputs to the design also becomes easier. And system Verilog makes collecting the outputs also easier, comparing them against expected output values also easier. So essentially, our intention remains same when we are moving from Verilog to system Verilog to UVM. Our intention doesn't change, and what we want to do also doesn't change, but the things become easier. So generating stimulus becomes easier, and driving those inputs to the design becomes easier, collecting the outputs becomes easier, and comparing those outputs against the expected output values also becomes easier. Why all this becomes easier is the language comes with more constructs. Now, as we go forward, I'll also explain about UVM. UVM also brings in more convenience compared to system Verilog, and how UVM does it, we'll discuss in later sessions. So that is what I mean by here. That is one of the course prerequisites. Then you should understand what is meant by a test case. Test case is nothing but a stimulus that we apply to check the design. One set of stimulus is what we call as a test case. Then other prerequisite is you should be comfortable with basic operators, assignment operators, comparison operators, shift operators. There will be those kind of basic operators you should be comfortable with. Okay, like comparison operators. If I tell you what is difference between this and this operator, can someone tell me what is the difference between what is this kind of operator is called as?
First
Double
one is
equal is
normal
called as
operator.
equal is only. This is called as logical equality operator. Okay. What is triple equality is called?
Case equality.
Case equality operator. It will consider X
Case, it is called as case equality operator. So what is the difference between these two operators?
Sir, in case equality, it should be compared.
Yeah, Anand, please go ahead.
That in case equality operator, it will consider the X and Z also, don't care, and high impedance also, but in logical equality operator, it will not consider.
Okay, anyone else? I think Tamal, that's not exactly correct. You said they won't be don't care. They will also be considered for comparison purpose.
It compares as zero.
If
Nirmohan, please go
there
ahead.
is
Okay, fine. Let me explain you. I mean, for others who are not comfortable with these things, don't mind. We will be covering these things in our language training. I mean, when we go to the system Verilog, there is a dedicated topic called as operators. There we will be covering. Why I brought up this topic is even these some of these operators, what I'm talking about, assignment operators, equality operators, are part of the Verilog language. So my expectation was that you should be at least comfortable with the basic concepts of these operators. Okay, so in this case, just to complete this question, what is logical equality operator would mean? Let's say if I declare reg 3 down to 0, a comma b, if I write a equal to 40 b 10xz and b equal to same thing, let's say. If I do, let's say reg c, I have one more variable called as reg c. If I write c equal to a equal to b, can someone tell me what will be the value of c?
1.
that don't care here, don't care.
It's not called as don't care. Answer is called as, anyone else can tell answer?
Unknown, sir. X,
What?
X.
Answer will be unknown. Answer will be
Yeah.
unknown. Yes. So unknown is the answer. Same thing if I write equal to triple equal to, that is, we should not call it as actually triple equal to a case equality with b. That's how we should read it. So how do you read this statement? A case equality with b. That is how we should read it. So what will be the output?
One logical, sir. One.
Yeah, one.
Because
It's one.
so
Yes.
when you do case equality, it does case to case comparison, x to x, z to z comparison. It does. When you do logical equality, it whenever it sees x or z in either side, output becomes unknown. So this much comfort level I will expect with you from Verilog language. That will make your system Verilog learning a lot easier. Next. Basic working knowledge of GVim and Notepad++. I mean, how to work with GVim. What do you mean by how to working with GVim? Is shortcuts. Let's say I want to delete a word DW. I want to delete 3 words, 3 DW. Let's say you want to copy, paste something here. That level of comfort, a basic level of comfort with GVim, where you don't have to type everything. Let's say operator, I don't have to type. I just do O, Control P, it should fill. And that this level of comfort, and in GVim, if you go, there is a concept of recording. The function recording concept will be there, where you can record a function and execute those kind of steps. Any that kind of techniques which makes your programming quicker will always help with the course, because our course will be a lot focused on programming. I mean, we'll be developing a lot of examples. So anything that can help you do the things quickly will will give a lot of comfort to you with overall course. Okay. So that is, if you are not comfortable with GVim, let's say you are already comfortable with Notepad++, that's also good. But anything that you should be able to comfortably develop the code. And working knowledge of any one simulator. It can be QuestaSim, it can be VCS, or it can be NCSim, or even if you are comfortable with EDA Playground, and that is also good. What do you mean by any working knowledge of any one simulator? You should understand what is compilation, what is meant by elaboration, what is meant by adding waves, adding signals to the wave, and what is meant by simulation. This is one thing. First, you should know what is what. Second thing is, you should know options at different stages. Let's say I want to define a macro. At what stage do I define a macro? Can someone tell me, do I define it at compilation stage, elaboration stage, or simulation stage? Defining a macro.
It should be during compilation.
We should do it at compilation stage. Okay. Let's say I want to pass a argument, elaboration time argument. We want to pass some arguments to be read using $value $+args. I mean, those arguments will be read using $value $+args. So when should we pass those arguments?
Elaboration during VC.
Basic.
Runtime.
During elaboration, we should pass them. Right? I want to pass a seed. Pass a seed value. When should I pass?
Simulation.
Simulation.
Via VSIM command.
Pass a seed value.
Simulation time.
Simulation.
Simulation.
Elaboration. I will explain you all this. See, what I mean by this is Verilog. Let's say I'm using QuestaSim tool. Verilog top.sv. Here we write width plus define plus width. So we are defining a macro here. Let's say I want to define another macro plus define plus depth equal to 20. So two macros I'm passing here. For those people who are new to QuestaSim tool, Verilog is a compilation command in QuestaSim, and vsim is a elaboration command. Vsim work.top. I mean, work is the directory into which all the modules gets compiled into. All the elements of the test bench gets compiled into work, and they are stored as a binaries into the work library. And top is the topmost module name. Here we can pass plus count equal to 20. That means you're passing a variable called as count that will be read using $value $+args. And if you want to pass a seed hyphen till Verilog, this is how we used to pass. Starting from system Verilog, we have something called as sv-seed. So whenever you see plus argument and minus argument, plus arguments, user has to manually use $value $+args to read it. Whereas the minus arguments, they are automatically read by the tool. What does it mean? Let us take one example to understand that. Let's say seed.sv. If I take this, I have module top, end module. I have integer a, initial, begin, end. I have defined a module top. with integer a defined inside it. Now I am randomizing. Basically, I want to randomize a 5 times. That is my intention. Repeat 5 times, begin it. So how do I randomize? A equal to $random. This is how you randomize a. In Verilog, how do we use the concept of seed? Is we pass seed here. This is how we do it in Verilog. Then if you $display, if you do $display, a equal to %0d a. This seed is something user must provide either by declaring here, and either you assign the value here by giving some value. This is one possibility. Otherwise, user must pass it as part of vlog seed.sv. Sudipta, please be in mute. If you don't have any questions, please be in mute. You have any questions? Top is the topmost module name. This is called as elaboration. So this is called as compilation. This is called as elaboration. Here we pass seed equal to some number. If someone is passing, this argument is called as a plus argument, because after plus it is coming. The arguments, everything is coming after plus, so it's called as plus argument. So to read a plus argument, we have to write $value plus args. In that inside double quotes, we need to write this whole thing. If had it been minus, you should write seed minus. Had it been hash, you should write hash. Basically, it has no special meaning for equal, no special meaning for minus. What it does is, whatever after plus, whatever arguments, whatever things are there, it matches with those things here. So if I give an equal here, you should write equal here. Percentage D, you are trying to read this as a decimal. Where are you trying to read it into? You are trying to read it into seed. Now, had we given this as XYZ instead of seed, if I had given it as XYZ, then I should have declared it as XYZ. Understand? So if I declare it as XYZ, read it as XYZ and pass XYZ as the argument to the $random. Just to keep as a good programming practice, we will keep it as seed. Now if I run this example, I am done with elaboration. Then here there is nothing to add to the waveforms. So I don't have anything to add to the waveform, so I will not do any command for adding to the waveforms. Then I will run the simulation. Run -all. So what is that I'm trying to do here? We have discussed that there are 4 stages of a simulator: compilation, elaboration, adding signals to the wave, and simulation. So here if you see, we are doing the compilation, here we are doing the elaboration, and we don't have anything to add to the wave, so we are not doing anything. Then we are doing the simulation. So you should be comfortable with what is vlog, what is vsim, what is run-all. I will show you similar things in EDA playground also, how to do this. That will make sure that you get comfortable with how to run this entire flow. Okay. Now, to run this, I'll open QuestaSim. I'll show you the same steps using EDA playground also. So So I went to the directory where my files are present. Do run.do. So run.do is a file where I'm keeping all my steps and I'm just running it as a do run.do. You see, it generated a set of random values. A set of random values it has generated. If I pass a different seed now, some other seed, what is happening is that seed is being read using $value $+args. For the people who are new to this, it is similar to scanf in C language. Similar to that, not same. Then during the $random call, I'm using the seed concept. So if I run the same thing, you will see a different set of random pattern being generated. You can see this random values are different because you have passed a different seed. The same thing if I have to do in system Verilog. I'll save it as seed.v. How do we do it in Verilog? Now same, that is seed.v is Verilog. Okay. If I have to do the same thing in system Verilog, I don't have to do any of these things. I don't have to do any of these things. I don't have to do any of these things. Nothing. You just have to make it sv-c. That's it. It's same thing. Okay, now if I run this, so still the file name is same, right? Because I have done all the updates to seed.sv only, the file name is seed.sv only here. If I run this, see, it has given me a randomization pattern. If I now again go and change, it has generated. Wait, it should have taken equal $random -sv seed. Wait, sv seed. Oh, that's okay. I think it does the. We still have to pass 1 minute. Let me just change once again. Which is generating the same. Okay, so there is a correction from my side. One correction for $random, we still have to go with the concept of seed only. At least as far as QuestaSim tool is concerned, it doesn't work. It should have worked for object randomization. I think, let me not confuse you too much with this thing. So what I was trying to tell you here is system Verilog kind of makes it easy for us. I mean, you don't have to go through $value $+args and all that. System Verilog has a mechanism where it reads these arguments automatically. Okay. Now, why we are not seeing the difference, I will explain to you in a later session, because I don't want to introduce advanced topics in this session. Okay. Let's get back to the original question. We were talking about simulator and various steps. So we discussed that simulator has various steps like compilation, elaboration, adding signals to the wave, and simulation. And we should be comfortable with, we should understand what is meant by these things, what is compilation, all these things. Then we should know what do we mean by various options we pass at the different stages. When do we define a macro? how do we pass the arguments during elaboration? What is meant by plus argument? What is meant by minus argument? What is meant by plus argument and minus argument? What is plus argument? Plus argument must be sampled, must be read using $value $plus args. Whereas minus arguments, the tool automatically reads those arguments. If I write vsim -no vopt -svseed, then I write work.top. Tool here, tool automatically read -no vopt and -svseed. It knows that -no vopt means run elaboration without optimization. -svseed means it understands that user is providing me a seed to use for randomization purpose. So please understand the difference. When I give plus argument, it is something user has to use $value $plus args to sample those, to read those arguments. In case of minus arguments, user just has to define those arguments and pass the corresponding values if required. The tool automatically reads those arguments. Those are called as minus arguments. Now you may say, can I give minus xyz as an argument? You can't do that because there is no meaning for xyz in the tool. So you should only pass the arguments which are relevant to the tool. Do you have any questions till this point? Okay, so that is all part of the course prerequisites. So working knowledge of any simulator or working with EDA playground. So I will explain you how to do with EDA playground in some time. Next, coming to the next aspect, the course assignments. As I said, overall course is for 7 weeks. This language training, a system Verilog language training part of the thing course. This will consist of 16 assignments. That is all part of our e-learning portal, which you will be getting access to. You will be getting access to the e-learning portal, where you can find all the course assignments, and we will also provide you with the guidelines how to submit these assignments. So this is the course you will be getting access to. So this is where you will find all the assignments. Once you log in, initially the very basic assignment, which checks your comfort level with GVim and EDA playground, then literals, the basics of system Verilog arrays and queues, then operators, the class and object oriented programming, the data type, task and function, fork join, inter-process synchronization, constraints, the functional and code coverage, assertions, DPI and callbacks, array methods, and you can also find the course presentation here, and the course material and system Verilog notes you can find here. So you can see almost around 15 or 16 assignments are there. Here you can see 15 assignments are there. So these assignments need to be done in 7 weeks. It's roughly 2 assignments per week. Should be completing. I would request everyone to spend time outside the training hours also to focus on these assignments and get back to me with any questions. And if you need any dedicated support in completing these assignments, you please let us know. And for other people, we will have dedicated lab sessions to support with the assignments also. Okay. So please keep this in mind that you should be completing 2 assignments per week, and that is where you will be in sync with the 7 weeks training flow. Otherwise, if you, let's say, if you start off with assignment 1 after 5 weeks, you almost will be towards the end of the course and you would be doing the basic initial part of the system relax. So I request everyone to spend additional hours and make sure that you are completing your assignments as per this. And assignments will be quite detailed. If you take any assignment, it will be quite detailed, where the question itself will be very elaborate to give you the intention of what to do. And you can always post your queries related to any question, or if you need any support, we can always take up those support during the live training sessions. And you can submit your assignments to submit.vlsiguru@gmail.com. Okay, and these assignments are focused on the practical uses of system Verilog language constructs, and student will gain good exposure to system Verilog. These assignments will make sure that you become expert with system Verilog. And there will be an evaluation towards the end of the course. Based on that, a certificate of course completion will be issued to you. Okay. Now the course material, you will find all the course material as part of the e-learning portal itself. Here itself you will get assignments, the notes, the course materials, the presentation, everything you can find in this portal itself. Next, what is the expectation from the participants? Is you should complete assignments as per the schedule, and please be proactive in the sessions. That is what I mean, respond during the sessions and make the sessions interactive. Both are same. I just wanted to emphasize what is the importance of being active in the session. Okay, now let us start off with the training. So we'll be taking a break once every hour or so. We'll be taking, let's say, we might take break around 10 o'clock. Okay, another 10 minutes we'll continue, and then we'll take a break. Okay, we'll start with the functional verification overview. Okay, we'll be quickly walking through this initial part of the training because we want to directly jump into system Verilog training objectives. I assume that most of you are familiar with the basic concepts of functional verification, so I won't be spending a lot of time on this. So this is the overall agenda. I mean, we'll start off with understanding what is functional verification, why we are learning system Verilog. The first question why we are discussing this topic is to understand why we are learning system Verilog. I mean, only then you will be able to appreciate the system Verilog language. Okay. Next thing is why system Verilog is easier actually. That is something we'll also be discussing compared to Verilog. These are the two things that we want to focus and cover in the next few minutes. Okay. Then once we are done with that system Verilog course objectives, understanding functional verification, then we'll talk about Verilog language constructs and shortcomings. Then we'll get into the system Verilog language constructs. Now let us start off with functional verification overview.
Srinivas, sorry for interrupting.
Yeah.
Will you be sharing that notes that you are taking? You are actually typing, right?
I will be sharing
so that we will not spend time on making notes in the.
Yeah, you don't need to make a notes. I'll be sharing all these notes to you.
Okay, fine. Thank you.
So let's start off with a quick overview of the functional verification. What is functional verification? The process of validating the design functionality against the design specification is what we call as functional verification. So we have an RTL code or behavioral code. We are checking whether that RTL code is working as per the design specification or not. That is what we call as functional verification. So what is the primary responsibility of a functional verification engineer? If I ask you, what is the primary objective of functional verification engineer? Can someone tell me?
Verifying the design done in Verilog using system Verilog with the design specification.
Yeah, basically, it all comes down to check the design functionality against the design specification. That is what it comes down to, right? Then what does it further comes down to? I mean, this is the requirement. Check the design functionality against the design specification. It comes down to catching as many design bugs as possible. I mean, he wants to prove that something is wrong with the design, and that wrong thing is called as bug. What is meant by a bug? Let's say there is a code, Verilog code, where data underscore OE underscore D should be 1, but RTL engineer, the person who has developed the Verilog code, has put 0 instead of that. That is one part of a bug. That can be a bug. So the role of a functional verification engineer is to catch those kind of issues. Okay. So some of us might feel that test bench development, some of us might feel what else? Implementing various components like generator, BFM monitor. That is all not what is the primary objective of functional verification engineer. Primary objective of functional verification engineer is always catching as many design bugs as possible. So the things that make it possible is the developing the test bench, developing test bench component, and of course the overall concept of features, scenarios, test plan, everything helps. But this is what is the main target always remains. Next. So functional verification engineer main role is to what? Catch the functional issues. He gets 2 inputs. One is design specification is one input, and the second input is the RTL code. It is developed by the design engineer and the integration engineers. The verification engineer develops test bench to make the functional verification more process oriented. Means randomly going and checking in RTL code whether it's working or not. Instead of that, he follows a processed approach where he develops if this is the design, around the design he develops a test bench. From the test bench he applies some scenarios as per the various test cases, and then he checks whether the design is working properly or not for all those inputs. That is what we mean by process oriented approach. So as part of that, we develop the various test bench components. Now, what are the various types of functional issues are possible? Can someone tell me? Functional issues can be 2 types. One is the bugs due to the wrong understanding of the design specification. You have read through the design specification and you have understood it wrongly. And because you have understood it wrongly, the design has been coded wrongly. I mean, who has done this mistake? Is it done by RTL engineer or verification engineer? Can you tell me?
RTL
when
engineer.
I say bugs, it is done by the RTL engineer. RTL engineer has read the specification and he has understood it wrongly. So because of that wrong understanding, he has coded it wrongly. Can you please read the second ones? Okay, next. The second thing can be bugs due to wrong coding. That is the coding mistakes, and you know that either both of them are possible. See, generally what happens when you go to the projects, the specifications most of the times are not matured, they won't be complete. So they will be still be under development phases, and that always leads to a scenario where you don't have the complete specs, and your understanding of the design is also not always proper. So based on that, you may have done some wrong coding. That is the one type of bugs. Other is, while coding thousands of lines, it's always possible to do some mistakes where instead of 1 you have written a 0, and that becomes a bug, design bug. So that is where the role of a functional verification engineer comes, where he develops a test bench and develops test cases to check these kind of, detect these kind of issues. Now that is where we require simulators. So I'm sure you all understand why simulators are required as part of verification. The verification engineer develops and simulates the test cases. For this, we require a simulator to run the scenarios as part of the test case, and to check the design behavior, we require simulators. Then the question comes, why functional verification is very important. Functional testing, if you see functional testing, I mean, what is meant by functional testing? A phase where we detect the functional issues in the design. The functional testing happens only at 2 stages in VLSI design flow. One is at functional verification stage, one is at post silicon validation stage. You see, if you understand complete VLSI design flow, it consists of roughly 12 steps. I mean, this number is variable, but as per me, let's say we call it as 12 steps, which starts from market requirements, the product requirements, till we do the fabrication and post silicon validation. Product requirements, fabrication and post silicon validation, 12 steps are there. In all these steps, in between comes physical design, in between comes static timing analysis, then comes layout. Various steps will come here, somewhere here DFT will come, synthesis will come, various aspects are there. Before that, RTL design, RTL integration, then you have functional verification, various steps are there. So in all this, what I'm trying to tell is, among all these 12 steps we are talking about, there are only 2 steps where the functional testing can happen. One is functional verification, one is at the post silicon validation. If functional verification does not happen properly, if we don't do the functional verification properly, bugs will be left undetected in the design. So design will still have the bugs, they will go into the netlist. See, you know that there is a concept called as synthesis, where the RTL code gets converted into gate level netlist. Those bugs which are undetected will go into the netlist. Physical design will be done on the wrong netlist. STA, static timing analysis, also will be done on the same. Fabrication also will happen with the wrong netlist. So finally, we'll be manufacturing a functionally wrong chip will be developed. A functionally wrong chip will be developed. Many times, even one chip going wrong, I mean, the one functional bug can lead to the company's closing down, because that is so much investment goes into one flow. I mean, say doing one flow of a chip actually. I mean, to execute this one flow from product to fabrication or post silicon validation, companies spend millions of dollars. So again, redoing the whole cycle will again require almost similar amount of investment. That is where a bug can even lead to companies closing down. So if a functional issue is not detected at this stage, if it is not detected at this stage, what do we mean by this stage? It will never be caught at any of these stages except for this stage. So the chance is that if you have missed it, you have missed it almost, unless it is caught at post-silicon validation stage. And the cost of detecting a bug at post-silicon validation stage is very costly actually. I mean, you figuring out some bug at post-silicon validation stage is very costly. So any questions till this point? I'm trying to give the importance of functional verification. So what I'm telling is the design issues can be caught in two stages: functional verification stage and post silicon validation stage. In case you miss detecting the bug at functional verification stage, the chance of detecting somewhere else is very minimal, because none of these target the functionality of the design. They are meant for something else. So hence functional verification plays a very important role in the entire flow. So what are the factors that drive the functional verification? First main objective of functional verification is to catch all the bugs in the RTL code. The factors that drive is less time in setting up the test bench, more time in developing test cases and debugging those test cases, running those test cases and debugging the design failures. So the primary driving factors of functional verification is less time in setting up test bench, more time in developing test cases and debugging those failing tests. So that is where we are moving from Verilog to system Verilog and system Verilog to UVM. So we will take a break here. Around 15 minutes break we'll take. We'll meet by 10:20. Once we meet after the break, we'll continue to understand why we are moving to system Verilog and why we are moving to UVM. Then we'll directly jump into the system Verilog language constructs. So let's meet at 10:20 a.m.
This conference will now be recorded.
So before the break, we were discussing about the basics of course, and then we started off with understanding what is functional verification and what is the significance of functional verification. So we were discussing that two of the driving factors of functional verification is less time in setting up the test bench, more time in developing the test case and debugging those test cases. So that is where we are moving from Verilog to system Verilog to UVM. So how does this help? Let us understand. Let's say we have one design, USB controller verification. Let's say we are working on a USB controller functional verification. Using Verilog, let's say if it takes 6 months time to do the verification, same thing can probably be completed in around 4.5 months using system Verilog. Same thing with UVM, might get over in 3.5 months. Again, it's just a might. Okay, there's nothing that tells that 6 will definitely become 4.5 months and 4.5 will definitely become 3.5. But the reduction will always be there, compulsory. How it happens is system Verilog, as I told you, provides lot of more language constructs, which makes all the aspects of test bench development easier. You take any aspect of test bench development, everything becomes easier because of more language constraints. What does it mean? What do you mean by providing more language constructs? Let us see. I'll take a couple of examples to show you. Okay. Example 1. Let's say if value dot su module dot end module integer a. Let's say I have integer int array of 1 9 down to 0, int array of 2, let's say 5 down to 0. Then you have b comma c. Some variables are there like this. See, I have declared one integer a and two integer arrays and two integer variables. Assume that these integer arrays, let's take a smaller values right now to keep our overall coding easier. Int a1 has some values, let's say 0 is 10, like that we have declared. 3. Let's say 20, 30, 40. Int a2, same way, we'll declare let's say 5, 15 and 37. Some random values, okay. B is equal to 20, C equal to, let's say B equal to 40, C equal to, let's say 50. Some values I have taken like this. If I want to check, my idea is to check if A value matches with any of above variables. Means what are variables? Int a1, int a2, b or c. What is my intention? If a value, whatever is the value of a, matches with either of these elements, either of these two elements, and b and c, one of either of them, that is my intention. If I have to do it using Verilog, how do you do that? If I have to do it in Verilog, how will I do it? I will write a code like this. If I'll write first a for loop. If I have to do that, I'll write a for loop. I equal to 0, I less than 4, I equal to I plus 1. Then I will check if condition. If a is equal to int a1 of I, then I will say that matching flag equal to 1. Means assuming, what does it mean? The value is matching. Similarly, I'll write one more for loop. For what? One more for loop is for what? Can someone tell me?
Int a2.
It is for int
A2.
So I'll write
A2, B and C.
A2. Okay, I'll do this. Then one more if condition. B A equal to B. I'll write one more thing for B. Or A equal to C. Like this, I can merge both of them and write in same thing. Then also I'll make matching flag equal to 1. Means if either of these three things are working, I will be setting matching flag equal to 1. So I hope you are understanding the intent. My intention is to check whether A is matching with any of these elements. If I have to do with Verilog only, this is all I have to do. The matching flag will tell me if it is 1 means it will tell me the value is matching, mean it is matching, else it will tell that value doesn't match. If I have to do it same thing in system Verilog, I have to write if A inside int a1, int a2, b comma c. That's all. Then I can say matching flag equal to. So this is what system Verilog does for us. This is one of the example what system Verilog does for us. Then what would have taken almost 13 lines of code can now be finished in 2 lines of code. See, it takes us only 1 or 2 lines of code. Instead of writing this kind of elaborate code where you are checking for each and every index, you can just check this kind of things. It will still do the same work. Whatever you have done here, this will do exactly the same work for you. Nothing, no difference. Okay, don't think that we are losing anything here. So system Verilog is about this. By providing more language constructs, it is making the programming easier. It is making it easy for us to develop various aspects of test bench development. This is just one example. I can give you hundreds of such examples where the overall coding effort can be reduced and it can be more straightforward. See, it looks more easy to read also what you are trying to do. So this is what system Verilog is about. So now initially speaking, this looks maybe easy, but eventually as you go forward, you will see that this is much better. Only what is the difficult part of system Verilog? Learning what is meant by inside, what is meant by flower bracket, why we are keeping flower bracket is what is the only complex part. Otherwise, everything else is easy. If you see, this is probably for some of you, this is the first time you are hearing the concept of inside and this flower bracket, this concept. This is called as set membership operator. It's called as set membership operator. So where it checks, it matches with any of these elements. Like this, system Verilog provides many more language constructs to make the test bench development easier. That is why the 6 months time comes down to 4.5 months. And when it comes to UVM, the same 4.5 months becomes 3.5 months or so. Even it could be less also. It further provides, UVM provides pre-implemented classes, which user can use to develop the test bench components. So in summary, user don't need to start from scratch, don't need to develop components from scratch. Whereas if you take Verilog and system Verilog, everything need to be developed from scratch. Whereas in UVM, there is no need to develop components from scratch. They are already pre-implemented classes. Using those, user can develop the test bench component. That is what reduces the overall coding effort. Now, that is not only thing. There are few more things that makes UVM very good for test bench development. I don't want to introduce everything now because it unnecessarily complicates our initial part of the training. So just remember that this concept of pre-implemented classes and some other concepts which makes the UVM easier for test bench development purpose. Since we are able to spend less time in setting up test bench by using system Verilog and UVM, it would automatically mean what? You will be able to spend more time on developing the test cases and debugging those test cases, which would automatically give you a better quality RTL. Since you are spending a lot of time on developing test cases, so your chance of catching the bugs will be a lot higher when you move to system Verilog and UVM based verification. Okay, so what is this page summary is what? So functional verification is not about test bench development, is not primary goal. What's the primary goal? Main objective is to catch as many bugs as possible. To do that, spend a lot of time on test case development. To do that, spend minimal time on test bench development. So that is where we are moving to system Verilog and UVM are useful for this, or making it happen. I hope this is all clear to you. Next. Okay, so I will skip some part of the things because I wanted to introduce the concept of SOC, subsystem, and modular verification. As of now, it wouldn't be. This slides doesn't make much significance, so I will skip those things. We will directly jump to this concept. What is the test bench development is about? Test bench development is about modularity and reusability. Why don't we code complete test bench in single class or single file? Generally, when you develop test bench are developed for modularity and reusability. What is meant by modularity is the concept of dividing the test bench into various subcomponents based on the functions they need to support. If you take a typical test bench, they don't develop. Let's say this is the design. For this design, we are developing this test bench. This is the overall test bench. So as a practice, we don't develop this whole test bench into single file. So if you see in Verilog, most of the test bench goes into single module. In this, whatever this thing you see here, this whole thing will constitutes of a single module in Verilog. And Verilog is completely more focused into task and function based code. If you see, some of you who have done memory verification, memory test bench in Verilog, can you tell me what is that we did in memory test bench to make the code more reusable?
We used a task, sir, to make it more usable.
Task and functions were used to make code reusable. But at the end, we created only one module only. The test bench was only one module. Whereas when you go to system Verilog, what system Verilog does is, system Verilog recommends that divide the whole test bench into multiple components. See, in Verilog, do everything in one place only. Verilog test benches, do everything in same module, but do them as separate tasks and functions. That is how you bring in the concept of reusability. In system Verilog, do everything in different components, not in same module. So once you have done them as different components, then the concept of separate tasks and functions are not required, right? Because you're anyway dividing everything into different components. What is meant by everything? What is that everything? Everything refers to. When we say everything, what is that everything is referring to? What do we mean by that? It is generation of scenario. You want to generate the scenario, right? That you want to apply to the design. You need to generate a scenario. Driving scenario to the design. Monitoring design inputs and outputs. Doing the various types of coverages, doing functional various types of coverages. Mostly functional coverage in this case on the design inputs. Then estimate, predict the design output and compare this output with actual design output. And finally, keep track of how many matches and mismatches. Based on that, report the test status. Basically, whenever we want to develop a test bench, this is all what we want to do, right? So I told that do everything in different components. That is what system Verilog encourages. But when we say do everything, what is that everything is about? It is about generating the scenario. Do it in a separate component. Do it in a separate component. So that component will be called as scenario generator. As the name tells, something which generates the scenario is called as what? Scenario generator. Something that drives the scenario to the design will be called as what? Can someone tell me?
Driver.
It will be called as the driver. Or sometimes we call it as BFM, bus functional model. What this component will be called as?
Monitoring
design inputs and outputs. It will be called as monitor. Next, doing various types of coverages on the design inputs. Design applied inputs. What is that called as? Coverages, doing various types of coverages. That will be called as coverage block. I don't need to give the name block because everywhere block is there. Scenario generator block, driver block, monitor block. So I don't want to again additionally give block. Block is already there. Okay. Predict the design output. What do you think that who will be responsible for that?
Predictor.
You can call it as predictor. More clearly, we can call it as reference model. Generates the reference output. Basically, predict means it is generating a reference output, right? So hence we'll call it as a reference model. Compare this output with actual design output. Tell me what is that will be called as?
Checker.
Checker. Next, keep track of how many matches and how many mismatches. Based on that, report the test status. What is that called as?
Scoreboard.
It is called as scoreboard. It keeps track of the scores. How many matches have happened? How many mismatches have happened? Whether test is passing or failing. That is called as scoreboard. Now what we will do is, let us put together everything and come up with the how test bench will look in system Verilog and how it will look in Verilog. See, in Verilog what happens is, if this is my design, DUT, design under test, and if I develop my test bench, I keep everything in same test bench. So this will be the test bench in Verilog. All test bench features are implemented in same module only using task and functions. Understand? using task and functions, we implement everything into the same module. What do we mean by that is, you take some of the examples. If I take a test bench memory, a small example. So I have opened a test bench for a memory. The test bench is developed in Verilog language. Starting from declaration of the ports, instantiation of the DUT, generation of the clock, applying of the reset and releasing the reset, and implementation of the test cases. See, we are implementing various test cases here and applying various types of scenario, front door read, then front door write, backdoor write and backdoor read, various types of things. Everything is done into the same module. Understand? Everything in Verilog based test benches goes into a single module under module TB. That is what Verilog promotes. But how Verilog improves that further is by introducing the concept of task and functions. Whatever you do in Verilog, you implement them as various tasks. Task 1, task 2, task 3, task 4. 4 tasks are there. By using those tasks, you have implemented various test cases. This is the best thing you can do in Verilog. I mean, this is the at best what you can do in Verilog. Understand? I mean, dividing the test bench into various task and function is the task and function is the only best thing, is the only and only best thing we can do in Verilog. Because you may ask, why don't we divide them into different modules? Why can't we keep them as 5-6 modules? The overall connectivity, everything becomes very difficult, because in Verilog, connections have to be done through module level. We have to connect at port level. That makes the whole division of the test bench into various modules very difficult, cumbersome task. Whereas when we go to system Verilog, and just to complete this one, these two are connected using port level connections. This is what? Port connections. This is how it works in system Verilog. In Verilog. This diagram is for what? Verilog. All test bench features are implemented in same module using task and functions. Whereas when I go to system Verilog, if this is my design, assume that it has got two interfaces. One is a interface through which you provide the inputs to the design. Assume that there is an interface through which we get the outputs from the design. Let's assume that this is our design. So design having two interfaces. Design with two interfaces. Even earlier in Verilog also, even if you have two interfaces, your mod test bench will still be same. Only single test bench will come. When it comes to system Verilog, what we are going to do is, primarily we are going to divide everything into different components based on what they are supposed to do. For example, you want to drive the scenario to the design. So since you want to drive the design scenario to the design, it should be the immediate component. It should be the immediate component here. This we call it as BFM, or bus functional model, or a driver. See, I told you either driver or bus functional model, that is BFM. Then we create one more component called as generator. This component is called as what? Generator. So generator and BFM are connected using a mailbox. Generator and BFM are connected using a mailbox. What is mailbox? Why we are using mailbox? We will discuss as we go forward. This is called as mailbox. Inbox. So mailbox is like a postal mailbox where generator puts something and BFM gets that elements. It's like a FIFO, first in first out kind of structure, where generator is putting the elements into it and BFM is getting those elements from the mailbox. So we have done two of the things. What is the third thing we want to develop as per the list? Can someone tell me? Monitor the design inputs and outputs. If you want to monitor the design inputs and outputs, what do we need? We need a component here, what we call as monitor. So to monitor that, we'll give one connection here. This we'll call as a monitor. Then this side also we need a monitor, right? Because we are monitoring this side also. We need a monitor this side also. So that is this. Another monitor. Then you will require a slave model. The slave model is required because whenever some transaction happens here, someone should respond to the transaction. If there is no one to respond, this transaction won't happen properly. It's like imagine a laptop where you are sending a transaction on the USB port and there is no pen drive connected here. Then will this transaction complete? The transaction won't complete, right? We have to connect some kind of model, either pen drive or something, that will make sure that whatever request I'm sending, I get response back to them. That is the role of a slave model, to respond to the request coming from. Then what is the next component in the list? Coverage block, right? I have to do coverage. The coverage will come here, somewhere here, coverage will come in. Functional coverage, it's called as functional coverage. Again, these two are connected using a mailbox. See, these two are connected using a mailbox. I'll have to keep a mailbox here. I'll call it as mbox, mailbox. Here mailbox won't be required because we need to do coverage only on the things that we are generating. See, we need to do coverage only on the things that we are generating to the design. So here coverage won't be required. Once it is done, what is the next component in the list?
Reference model.
Reference model, right? So the reference model will develop somewhere here. I'll just change color, or let me keep red color only. It will be easy for me to explain overall thing. So here I'll keep reference model. This reference model is connected from monitor again through a mailbox. There will be a mailbox here. And this is giving you what outputs? What outputs is it giving? It is giving me expected output. The expected output. Expected design output. I'll call it as expected OP. This is giving me what output? If I am applying an input here, if I am applying input, what is the output I am getting here? The
Actual output.
Actual output.
Actual output.
That is being monitored by this monitor. So that means monitor is collecting the actual output. This is giving me expected output. Now, as per my flow, what is the next component I need to develop?
Scoreboard.
I need to
Checker.
develop
Checker. Yeah, checker. Yes, checker.
So the checker will be somewhere here. Checker will be somewhere here. So this will be the checker. And this connection will go here as another input. This would be a mailbox. And the checker will give the outputs, whether the match has happened or mismatch has happened, everything it will tell me. Those outputs will finally go to which component? What is the next component in our list, if you remember?
Scoreboard.
Scoreboard.
Checker board.
Yeah, it's a scoreboard. Scoreboard. Scoreboard.
Require a scoreboard. So this connection is there between checker and scoreboard. So finally, scoreboard will see the number of matches and mismatches and tell me whether test is passing or failing. So scoreboard is like a cricket scoreboard, checker is like a cricket umpire. So the umpire will tell whether it's matching or mismatching, whatever. Based on that, scoreboard displays the results. Going forward, we will also see that there will be one more set of components called as assertions. One more set of components called as interface level assertions will be there. That is connected here. They will be called as assertions. Here also assertions. That will be again connected here. Okay. This overall thing is what we call as the test bench architecture. And the final goal of our training, whether we do it for 3 months, whether we do it for 6 months, whatever, is to be able to develop this kind of architecture using one of the languages. It can be Verilog, System Verilog, or UVM. Now you will realize that developing this test bench using Verilog is very difficult. I mean, if someone gives me this above test bench architecture, someone gives me about test bench architecture diagram and ask me to develop in Verilog, it is very difficult to do. Why? Because see, the concept of implementing it as a module, see, in Verilog everything is a module, right? This is a module, this is a module, this will be a module, this will be a module. The overall connection of two modules, the connection of two modules, it's very difficult. How do you connect one module to another module in Verilog? Can you tell me what is that we use?
Using port mapping.
Instantiation.
Using port mapping we do. See, we use some nets here, N1, N2, N3 here. Again, using the N1, N2, N3 here, we connect these two ports. That concept of connection of modules in Verilog is very difficult. So hence, Verilog doesn't recommend or I would rather say doesn't support a test bench architecture with lot of test bench components. Why? Major reason is what? The connectivity of connecting those components is very difficult. Connecting those components is difficult actually. Is at port level, and it's difficult. It is difficult to do. System Verilog is good at developing these kind of test benches. How it does is, it comes with a concept called as class. Generator can be implemented as a class. BFM can be implemented as a class. Monitor can be implemented as a class. Functional coverage can be implemented as a class. Reference model can be implemented as a class. And all those classes can be connected using a structure, a FIFO kind of structure called as mailbox. Okay, here checker can again be implemented as a class, scoreboard can be implemented as a class, monitor can be implemented as a class, and all of them can be interconnected using mailbox. Everywhere mailbox will be there. See, even here there will be a mailbox. Whenever you are connecting one component to another component in system Verilog, they all will be connected using mailboxes. So system Verilog is very good at developing this kind of modular test bench. See, whatever you see here is called as modular test bench architecture, where good at developing modular test bench architecture. What is meant by modular test bench is a kind of test bench development style where the whole functionality is divided into various components, multiple components, and those components are logically divided. See, it's not like we are taking half of this BFM, half of this generator and putting into one component and another half into something else, another half into something else. No, and we are not taking this and calling it something. So things related to generation of scenario will be called as scenario generator. Things related to driving the scenario will be called as driver. Things related to monitoring, anything monitoring related will be going into monitor. Anything related to coverage generation will go into coverage. So this kind of logical division we do of the what we want to do. That kind of test benches are called as modular test benches. As we go forward, you will see that this is a recommended style of test bench development because this approach makes it easy to divide the activity. See, I can divide this activity, I can give it to engineer 1. This is, I can give it to another engineer 2, engineer 3, 4, 5, 6, 7, 8, 9. If I have a team of 9 engineers, I can divide this whole activity into 9 sub activities. They will, one person will deliver me generator, one person will deliver me BFM. I will use a simple mailbox and I establish this connection. The third person will deliver me a session. I'll use this connection to integrate this into the test bench. The fourth person will deliver me monitor. I will again use this interface connection. Fifth person will deliver me functional coverage. I can use mailbox to connect. Like that, I can divide the overall activity and into different sub aspects. And another most important thing is, since they are modularly done, any mistake that happens here, any mistake that happens into this is not going to impact the rest of the things. Any mistake I do in, let's say, this monitor will not impact this, any of these things, because it will be only limited to that portion. So it is easy for me to pinpoint the things and update them. Now imagine a scenario where everything is coded into one single module. Let's say this whole thing is a single module. everything will be interconnected, right? Some mistake I do in some part of the code will impact something else because they're all in the same module. That is where we always wants to do modular test benches. Second thing is the byproduct of modularity is reusability. Byproduct of modularity is what? What does it mean? By keeping them as separate component, generator as one component, assertions as one component, BFM as one component. If I want to reuse generator somewhere, I can only take this component and reuse in some other test bench architecture. Somewhere I only want to reuse monitor. I have a separate file called as monitor. I can reuse it in different project. For whatever blocks you see, anything can be reused in a different project because all these components are coded as a separate set of files. Okay, so that is about how do we come up with a test bench architecture. Only thing is, given this test bench architecture, most of it can be done using Verilog also. I can do a generator coding using Verilog. I can do BFM coding using Verilog. I can do mailbox kind of behavior using Verilog. I can do monitor using Verilog. I can implement reference model using Verilog. Functional coverage we can't do because the Verilog is not meant for doing functional coverages. Except for this, everything else in this diagram can be done using Verilog. But the problem with Verilog is not good at these things. Even though you can do using Verilog, Verilog will not be able to give you a efficient test bench when you implement them separately. So rather what Verilog does, Verilog implements the same thing in single module by using various tasks and functions. Generation will become one task, driving will become one task, monitoring can be done as another task, reference model generation can become another task. All of them are put into a single module. Whereas system Verilog recommends developing everything as a separate components, and finally everything is connected using various mailboxes and interfaces. So this is how this reference test bench looks like. Next. Okay. Please read this once. So as we were discussing, so the test bench development in system Verilog and UVM is driven by the concept of modularity and reusability. So why don't we use complete test bench in single class or single file? basically the idea is test bench is developed for modularity and reusability. What is modularity? The concept of dividing test bench into various subcomponents based on the functions they need to support. We have already discussed about this. Dividing test bench functionality into different components ensures reusability of these components across different test benches. So what is meant by reusability? Let me again explain you. Let's say I'm working on one more design verification. Assume that this is the AXI interface. This interface is the AXI protocol. I have one more design, okay, where I'm verifying some other design. Let's say this is USB controller. Let's say I'm verifying a DDR controller. Let's say DDR also has AXI. DDR also has AXI interface. In that case, I can directly reuse these three components directly with minimal changes. I can reuse the BFM in DDR controller verification. I can reuse the monitor. I can reuse the sessions because these three components are developed specific to this interface. So hence we can reuse these components. That is all. Had we coded everything into one single module, the reusability of these things wouldn't have been possible. This is one benefit of modularity. Okay, I hope you understood this. Any questions so far? Okay, next. So this is how the test bench architecture looks like. Now, as I told you, Verilog for test bench development. See, Verilog is not meant for modular test benches. Why Verilog is not good for modular test benches? Primarily, Verilog was primarily meant for RTL coding. Verilog has very few features. I mean, it doesn't have many features, so mostly have features which are meant for RTL coding. I think I have already explained you. Summary is what? Verilog is not good for modular test bench development. Next, how about System Verilog for test bench development? System Verilog has a lot of new constructs added, like object-oriented programming, new set of data types and new set of operators, arrays, concept of inter-process synchronization, functional coverages, interfaces, program block, clocking block, mod ports, the concept of fork join with multiple variations, the concept of constraints and randomization, assertions, DPI, and a lot of scheduling regions. There are a lot of things that are added in System Verilog which are not there in Verilog. Makes the overall test bench development a lot easier. Essentially, all these things, in fact, this one thing is what makes the modular test bench development easier. Okay, so what is the benefits of modular test bench development? Can someone tell me? So, what is the benefit?
Build each element as module and reuse them in another cases also.
So the benefits is the work distribution. I mean, project management becomes easier. Okay, since work can be easily distributed. That is one thing. And one component implementation does not impact other component or issues. Implementation or issues doesn't implement other component because they are modular. They are different component. And since this helps with reuse. Code reuse. You can reuse the components. So developing a new test benches becomes easier. Developing new test benches using existing test benches becomes easier. So that is why we will be developing modular test benches. If you take a simple design like 2x1 multiplexer, you will realize that Verilog test bench is lot easier compared to system Verilog test bench. But if we take a complex design, then we will realize that Verilog test bench is very difficult. And system Verilog test bench will be relatively easy. Again, what I want to tell here is, during your learning, let's say you're taken 2x1 multiplexer as your design and you start doing test bench development, you will find that, oh, things were a lot easier in Verilog actually compared to system Verilog test bench. I mean, there you won't find the benefit of dividing generator, BFM, monitor, and all that benefit won't come. But as the design complexity increases, let's say we are talking about USB controller or PCIe controller, that level of complexity, even you don't even need to go to that level of complexity. Anything you go little fold increase in complexity, you will see that Verilog test bench is not good. System Verilog test bench is relatively easier. Next, UVM for test bench development. I will be quick here because my point is, even if I explain you everything, you won't be able to remember unless we do something in UVM. So I'll just quickly read through. I'll only tell you 2-3 guidelines. UVM, in this slide, we are understanding how UVM will be useful for test bench development. Basically, UVM is developed on top of system Verilog. It comes with a pre-implemented base classes. So it makes sure that verification engineer don't need to develop everything from scratch. It comes with a very well-defined guidelines on how to do everything in test bench. Let's say you want to develop a test bench architecture. UVM tells you how architecture needs to be developed. Let's say you want to do test case coding. UVM gives you the guidelines. For everything you want to do, well-defined guidelines are there. You just have to use those guidelines to come up with architecture, develop the test cases, develop the test bench components, do the test bench component connections, reporting messages, anything you want to do everything in the test bench. I have listed only 6 things here. Whatever any other thing that comes to your mind related to test bench development, there is a preset well-defined guidelines out there. In system Verilog, verification engineer has to develop all this behavior from scratch, whereas UVM provides with base classes and predefined guidelines for all above things. That is where UVM further reduces the time taken to develop test bench. See, in UVM also you will do the same things. If you ask me, does test bench architecture change in UVM? No, it will be more or less same. Only thing is, in system Verilog, if you take BFM, you have to start from scratch, developing class, BFM, end class, like that you have to code. In UVM, there is a base template available already for BFM. You just have to use that base template and update, do the required updates. That's all. The difference between SV and UVM, I'll tell you through a simple analogy. Okay, let's say if we talk about pizza making. Okay, if you see in houses, some people make pizzas also, right? So there are 2 ways. One is buy the bread, buy the pizza base bread, then add the required ingredients and make the pizza. So there are 2 approaches here. One is make it, one is buy it. So pizza base bread. So system Verilog is about you have to make it from scratch. and then use that thing. Whereas in UVM, you don't make it, it is already available to you. You just directly use that and only do the required updates. So you spend time, right, to make it. That time gets saved. So in UVM, you don't have to go through that process of developing the base common thing. Okay. Even in UVM, so coming back to again this thing, when it comes to making the pizza, like adding ingredients, the UVM will tell how to add those ingredients, in what proportion to add, when to add. I'm just giving you guidelines, okay? Don't literally take this. I'm telling you, UVM gives you guidelines, what to do, when to do, how to do, all those things. That makes the overall process a lot easier. In System Verilog, everything has to be done from scratch. It just that it gives you more language constructs, but developing each and every component, like developing the driver, BFM, generator, monitor, everything need to be developed from scratch. That is where the industry is moving towards the UVM. Next. Okay, just to take a quick review of what we have discussed so far. We have understood what is functional verification, the concept of functional verification overview. The term verification has different meanings for different engineers in VLSI flow. See, the functional verification, the term verification, you see, can have different meaning for different people. If you go to a backend engineer and tell that you are working in a verification, he will assume that you are doing a physical verification. So that's the reason term functional verification is important. You have to use always the term functional verification, because during the flow there can be various types of verification can be there. Then we have understood why functional verification is required. Then we have understood what are the inputs to the functional verification engineer. Can someone tell me what are the inputs to a functional verification engineer?
Design specification and the RTL code.
Design specification and RTL code are the inputs. Okay, various steps in functional verification flow we did not discuss because I didn't want to introduce and complicate the things. We'll discuss this as we go forward. Then do you all understand how do we develop test bench for a given DUT? Let's say we took an example of design with 2 interfaces and we have developed the test bench. Do you all remember how we came up with that architecture diagram?
Yes.
Yes, sir.
Okay.
Yes.
Can you tell me what are all the various components in the test bench?
Generator, scenario generator,
Generator,
BFM,
BFM, mailbox, monitor, assessor.
Generator, monitor, functional.
Yeah, so basically various components like what you see here. Generator, BFM. So what are the various components of the test bench? Generator, BFM or driver, monitor, coverage, reference model, checker, scoreboard, assertions, and slave model. How many components are there totally?
9, sir.
9 components. All our next 3 months of training or whatever training is focused on how to develop above 9 components efficiently. That's all. Our training is only about this. That's all. How to develop generator, how to develop BFM, how to develop monitor, how to develop coverage, how to develop reference model. Now the best part of this learning is if you know how to develop for a USB controller. Let's say if you know how to develop for a USB controller generator, the generator for PCI controller won't have different meaning. Will not mean something else. You're getting the point? Let's say in USB controller, generator generates the scenario. If you go to PCI Express, it is not going to do some other work. It's not going to do the work of a checker. It will still be doing the work of a generator. Only the functionality specific to PCI Express will be changed. Here the functionality will be specific to USB controller. So what I'm trying to tell here is, if you know how to develop a test bench for one medium complex design, then you can develop the test bench for any other design using the same guidelines. So that is something we'll be doing as part of the course, where we'll take one design and we'll be developing the complete set of components, and through that you'll understand how various components gets developed. And you should always, your learning should always be to learn the flow, to learn the concepts rather than memorizing the things. See, many times people, what they do is, if we teach one protocol AXI, component development. Actually, AXI is a complex protocol compared to APB. Same thing, if I ask them to do APB component development after learning AXI, they can't do. That should not happen. That you have only memorized how to do AXI component development and you can't do APB, which is much simpler compared to AXI. You should learn the concepts, how generator is being structurally divided, how it is being developed step by step, how that concept can be applicable to different protocol or different design. That level of understanding you need to develop. Simple, right? Over next 3 months, we are going to learn how to develop 9 components. To do that, we will be learning different language constructs, arrays, operators, functional coverage, assertions, different concepts we'll be learning. But our final goal remains same: how to develop these things efficiently. Okay. Next. Yeah, I told you, right? Scenario generation component. I mean, this whole test bench, 9 components, can further be divided into 2 categories. Components which are meant for generating the scenario. These are the components which are meant for scenario generation. Next is used for scenario generation and driving to the design. Next is components used for checking the design behavior. Monitor, reference model, checker, scoreboard, assertions, and slave model. These are used for checking the design behavior. See, one set of components used for scenario generation and driving to the design. That is one set of components. Other set of components which are used for checking the design behavior. Okay, so if I have to draw in this diagram, these are the components which I am calling as the components meant for generating the scenario. The other components, whatever other component you see these components, this component, this component, this component, these are all used for checking purpose, whether the design is working properly or not. To check that, we are using that. That is what I meant here. Components meant for scenario generation, components meant for checking purpose. Then you have learned the concept of modularity and reusability. What is meant by modularity? What is meant by reusability? Can someone tell me what is meant by modularity?
Breaking the entire test bench architecture into
different models,
so that we can divide the test bench work to different resources to speed up the process and code reusability.
Okay. Thank you. Yeah. So when do we close functional verification? We will discuss later. Right now, just to answer this question, this is not immediately important for you, but since I have given the question here, I want to complete that question. When to close functional verification? FV means functional verification. When we get 100% test case passing, 100% functional coverage, 100% code and assertion coverage. So when we get these three parameters 100%, all test cases should be passing. We should get 100% functional coverage. We should get 100% code and assertion coverage. Then we can say that our functional verification is completed. We'll discuss more about what is functional coverage, what is code coverage, what is assertion coverage as we go forward. I had taken some traffic light control example in previous slides, but I didn't discuss that because I felt that is not really relevant for you at this stage of time. So hence I didn't do. We can skip that question. Can functional verification be done with Verilog alone? Can someone answer this question? Is it possible to do functional verification to be done with Verilog alone?
Yes, sir. We can do it for simple designs, for very simple designs.
No, even for most complex designs, we can do verification with Verilog. But the only problem is it is going to take a lot more resources and lot more time. See, let's say you're using a mobile phone. You have a mobile phone in your hand, let's say. That mobile phone initially was developed as a RTL code, Verilog code. That kind of complex designs can also be verified with Verilog. But the problem is Verilog is not good for them. Because what might take 1 year with system Verilog will require 2 years time to do the same task, because Verilog is not good at test bench development and not good at implementing complex test scenarios. Is this clear to everyone? Tamal, is it clear to you?
Yeah, yes, sir. Yes, sir. I got it.
Yeah, okay. Then we understood how system Verilog and UVM helps. Already we have discussed. I think different types of functional verification we'll discuss as we go forward. There will be something called as directed verification, constrained random verification. What is those things we'll discuss, because I don't want to introduce way too many things in the single class. Okay. And how different types of functional verification differ, we'll discuss. Remaining things, how to use QuestaSim, I'll teach you as we go forward. And examples on basic data types and array operations. Some we just learned how to declare function sum and how to call the function sum. It was to make sure that you are comfortable in the very basic things of Verilog. Now we will take a break here. We will meet by 11:45. Once we meet after the break, we will continue with system Verilog training course objectives and other aspects further.
This conference will now be recorded.
So till now we have discussed about what is functional verification and why system Verilog and UVM are very important in the functional verification flow. We have understood, and our whole discussion revolved around developing modular test benches. That is our primary goal. We could have used Verilog, we could have used VHDL, we could have used system Verilog, we could have used UVM, any of them. But thing is, as I told you before, Verilog and VHDL kind of languages are not good for modular test benches. Verilog and VHDL are not good for modular test benches. Why am I repeating so many times is, I want to emphasize the importance. When I repeat multiple times, you understand it as the importance I'm giving to that specific concept. Okay, system Verilog and UVM are very good are right choice for modular test benches. So what is that makes them right choice? What is that keeps them aside? I mean, makes them right for modular test benches? Can someone tell me?
Object-oriented programming.
The concept of only one line answer is the object-oriented programming. System Verilog and UVM has this concept of object-oriented programming, which is implemented using classes, is what makes them so powerful actually. And it is very important concept for you, because for any engineer, for any programming, any engineer who does programming, whose job involves programming. Programming doesn't mean C++. Okay, programming could mean anything. Let's say Python. You're doing a Python programming. You're doing a Perl application development. You're doing a Verilog programming. It can be anything. Object-oriented programming always takes your programming level to a next level, where you are able to look at the overall environment at a bigger level rather than looking at a small level. You look at the overall test bench at a much bigger level, and you will be able to develop very efficient and modular test benches. In summary, wherever you go, whether you go to Python, whether you go to Perl, whether you go to C++ or System Verilog, anything, if you ask why people use object-oriented programming, the answer, one line answer is they want to do things in a modular style. That's all. Answer is what? They want to develop things which are modular. What do we mean by modular? Developing things in such a way that everything is implemented separately based on their functionality, and finally interconnect them. It's like dividing a house. Let's say I have a big room, and I can actually, what I can do, let's say this is a 30-50. I can use this whole thing as a one single room, I mean house, where everything is there only, kitchen, without any partition. What System Verilog does is it brings in the concept of modularity, where we divide it. One portion is kitchen, one portion is hall, like the different divisions we do, and then use that. But not like this, of course, in a square shapes. Okay, so that is what System Verilog does, and it is the object-oriented programming which makes it possible. I mean, if we are talking about the keyword modular test benches, that is happening because of the concept of object-oriented programming in System Verilog UVM. That concept will be there in any other language also. So this concept of object-oriented programming does not change when you go to Python, doesn't change in Perl. So once you learn in System Verilog the concept of object-oriented programming, the same concepts will be applicable in other languages also, with some name changes, some minor changes will be there, but otherwise lot of things are common. So I'm telling you that when you are learning object-oriented programming in System Verilog, give your best possible effort, so that when you have to learn the same object-oriented programming in Python, Perl, and C++, you should not have any problem at all. So give your best possible effort, do all the assignments, and give more time to do the assignments, and come back to me with your doubts, and make sure that you do more than what I ask you to do, because it will take you to the next level. Your overall approach, overall programming, everything will go to the next level when you become good with object-oriented programming. Again, I'm emphasizing it so many times because that is so much important. Okay, so I will make sure that, see, you may ask next question, do I need to know basics of object-oriented programming? Nothing. We will teach everything from basics, but only thing is the things will move quickly, so you need to spend time. spend enough time to keep up with the pace, the training pace. That's the only one line I will tell you. That is where if someone is not able to do better, that is because of this problem. They are not able to spend enough time. As long as you are able to spend enough time, training will start from the fundamentals for everything you learn. Okay, now let's continue with the session. So let us start off with System Verilog training course objectives. Basically, at the end of this course, you should be good with learning. You should be comfortable with all System Verilog language constructs. When I say language constructs, the concepts like operators, data types, literals, interprocess synchronization, various types of arrays, functional coverage, all these kind of concepts you should be comfortable with. And you should be able to write a simple test cases to check each construct usage. If I ask you to explain me mailbox, you should be able to write a simple environment file, simple code to tell me how mailbox behaves. Let's say if I ask you to explain interface clocking block, you should be able to write a simple test case or simple code to explain that construct uses. Exposure to on-chip protocols. I mean, based on the course you have enrolled for, we'll be teaching the AXI and AHP protocols. Basic overview of the peripheral protocols like PCI Express and Ethernet, and verification IP development for any given protocol, AX and AHP. And you should be good at developing SV based test benches from scratch for a complex design. I mean, coding all the test bench components, test bench coding and debugging, setting up regression and analyzing the regression results. This would be the final objective. So effectively good at developing simple test cases for various language constructs, good with the basic protocols, and develop the test bench components for those protocols, and ability to verify the complete design verification flow. Okay. We have already, now let's go to the next slide, need for System Verilog and UVM. Okay, can you please read this once? So see, so in this slide we are understanding what is the need for System Verilog and UVM. Basically, as you see, with every passing year, the complexity of the designs is going up. When we say complex designs, what does it mean? More number of features and more number of complex features. Basically, whatever features that are getting added into the electronic devices, they're all also getting complex. And to implement those complex features, we are using complex protocols. For all that reason, we need advanced languages, which makes the verification easier. And the second reason is time to market. Basically, how quickly we can launch the product into the market. Third is better project management. Means reusing of existing code. System Verilog and UVM are object-oriented programming based, which helps with the code reuse, and they helps with better project tracking. So these are the three reasons. So first reason is what? Growing complexity of the designs with complex features and complex protocols requires advanced languages like System Verilog and UVM. And to meet the time to market, third is for better project management. I mean, what is meant by better project management is you will be able to tell in System Verilog based test benches clearly, at this time I have done 40% of verification. After 2 weeks, you can tell I have done 65% of verification. Now let us say you are doing Verilog based verification. If your manager comes and asks you how much percentage of verification have you done, it's difficult to tell that number, except for referring to code coverage. Whereas in System Verilog, we have concept of functional coverage, assertion coverage, and code coverage. All these things gives us a very good measure of how much verification we have done. Next, running System Verilog code using QuestaSim. Please read this once. I will explain all these steps. Okay, so as I have told you sometime before that in System Verilog based test benches, we'll be running the code in multiple stages. We have discussed about compilation, elaboration, adding wave, and simulation. Now that can further be divided as you start off with creating a compilation library using vlibwork, and compilation where you compile your Verilog or System Verilog code into object files. Then we do mapping. There will be some concept of mapping, elaboration, and simulation. Various stages we go through. As we do some examples, we'll understand these things. And user can also create a do file to run all these steps in one go. We can create a do file. You remember I have created one do file here, run.do, where you are running all these steps into one single file, and you can just say do run.do, it will run all those steps. User can also do all these steps using GUI mode. Whatever I have done using the do file, all those things can be done in the GUI mode. GUI mode is preferred when one test is being run. Only if you have to run only one test, you prefer GUI. When a group of tests needs to be run them in a terminal. I mean, run them in a batch mode. So what is meant by GUI mode is there will be this symbol, using that you compile. There will be elaborate symbol. I mean, one option where you can elaborate. Like that. See, if you go to the module, you can go here and do, I think, library, right? I have to go to library. go to the module, right click, then simulate. That will do actually the elaboration. Then you can run the simulation by using these options. Sorry, there will be these options through which we can run the simulation. So why I am not getting deep into each of these is because since you are already familiar with Verilog, you would know what is meant by compilation, what is meant by elaboration, what is meant by simulation. So I don't want to spend a lot of time teaching that concept. Next, let us start off with understanding basics of Verilog language. So before we start learning any language, it's good to learn the basic fundamental concepts of the language. So now we will be learning System Verilog language basic concepts. Means we'll try to understand how it differs from Verilog. Okay, the first thing you need to understand is the concept of data types. Basically, data types are two types. Data types are two types. One is called as static data types. One is called as dynamic data types. Verilog only has static data types. Only supports static data types. System Verilog supports both static and dynamic. It supports both static and dynamic. Let us understand what is the difference between static and dynamic data types through this example. Then I will take an example to help you understand. Please read this once. So there are basically two data types. One is static data type, one is dynamic data type. In static data type, memory is allocated and fixed at the compile time itself. Verilog only supports static data types. What is dynamic data type is memory allocation happens at the runtime. It can be, the memory can be increased, can be decreased, can be deleted at the runtime. I will give you a simple example to understand difference between static and dynamic data types. You take a Ethernet protocol example. In Ethernet protocol, the Ethernet frame is having a length of 42 to 1500 bytes octets. This can be the length of Ethernet frame. In Verilog, if I have to declare, I have to compulsorily write it as range 7 down to 0. The payload. Payload means the overall the data of the Ethernet frame. 1500 I have to declare compulsory. Means we need to take into consideration the biggest possible size. Even if the payload size is 100 bytes only, see, since I'm telling 42 to 1500 octets, it can be 100 also, right? So even then my payload should be declared as 1500 octets only. 1500 size I have to declare. That means how do you declare in Verilog? 1499 down to 0. In system Verilog, I will declare the same thing. I can declare the same thing as range 7 down to 0. Payload $. That's all. Either $, I can declare. $, means it's a queue. Or I can declare it as a dynamic array. Without $, that becomes dynamic array. The benefit is both are equally beneficial. Benefit is if we want to create frame of 100 octet size, 100 octet payload size, I will do payload equal to new of 100. That's all. Only 100 elements gets used. 100 element space will be used. That is what makes it dynamic in nature. That is what makes it dynamic in nature. Now, if someone, others, can you hear me? Everyone, can you hear me?
Yes, sir.
Yes,
Yes,
yes.
sir, you are audible.
Yes, sir. Audible.
Okay. If we want to create, let's say, packet payload of 200 again, only 200 element space will be used. Okay. Now, again, if I go and do payload of new of 10, what will happen is that 200 will be reduced to 10 elements only. So the 190 elements space will get freed up. That 190 element space gets freed up. In Verilog, that is not possible. In system Verilog, all that is possible because of the concept of dynamic array and queue. That is what we mean by dynamic data types. So the memory allocation happens at the runtime. See, at the runtime, you're telling how much space you want to give, 100 space or 200 or 10. And it can be increased, it can be decreased, it can be deleted also. You can altogether delete that also. How do you delete it? Just say, go and say delete. The whole space gets freed up. This is the benefit of system Verilog. So tell me, this is Verilog. This is system Verilog style. Which one looks better for you? Which one is more memory efficient? Which one is efficient in terms of memory utilization?
System dynamic data type style.
So it is system Verilog, right? System Verilog is much more efficient because in Verilog, we have to always take into consideration the worst case size of 1500. Means you will be compulsorily keeping up all this memory space. Whereas in system Verilog, you will be able to choose, I only want 100 bytes. I will only use this. So this will be freely available for something else. It's like my laptop RAM, where I have used only 100 megabytes and remaining 900 megabytes or some space I'm not using. Someone else can use it. That way my laptop will work efficiently, right? Whereas if I keep all this space reserved for myself, my memory utilization won't be efficient. So that is where system Verilog is better. Now someone is asking line number 235. This line number 235, the concept of new. What is this new concept is? This is called as memory allocation. Whenever we work with dynamic data types, what is meant by dynamic data type is Q is a dynamic data type. Dynamic array is a dynamic data type. When we work with these kind of dynamic data types, we need to explicitly tell how much memory to allocate. How do you tell that? Here by giving new of 10, you are telling that allocate enough memory to store 100 elements. New means allocate a new memory space. See, it's all like I am using my laptop. I want to open an application and my RAM is there. I am telling through the application that allocate me 100 spaces in this RAM. So that 100 spaces gets allocated for my RAM. That is what when I do new. Please don't take this literally. Okay, I'm taking laptop example just because you will be able to correlate it easily. In this context, what I'm telling is I want to use payload. Right now payload has a different size. Now I want you to find 100 memory spaces for me, allocate them. So then you will be able to use the 100 elements of the payload. In summary, new is called as memory allocation constructor. It is also new is also called as a memory constructor. It allocates space for 100 elements. Mansi, is it clear to you?
Yes.
Okay. Someone is telling, is it similar to the concept of override? Override again depends upon in what context we are talking about override. In system Verilog, there is no override concept. If you are talking from some other language perspective, then I am not sure, but not exactly. See here, yes, if you ask here and here, override is happening. See, you had allocated 100 spaces. Now you are telling that override it with 200 spaces. You are telling override it with 100 spaces. If that is the context in which you are telling override concept, yes, that is same as override concept. Vamshi, is it clear to you? Okay. Next. So I hope you all understood static and dynamic data types. So Verilog has only static data types. So not efficient for memory utilization purpose. Verilog language is not good from memory utilization perspective, whereas system Verilog mix of both data types. Hence, it is good. It is very efficient for memory utilization. Okay. So going by that, which one will you prefer, Verilog or system Verilog?
System Verilog, sir.
System Verilog.
System Verilog. Now the next question comes: how do I know? How do we know what is static and what is dynamic? what it mean, which constructs are static and which constructs are dynamic? Which constructs?
Where the static is fixed and the dynamic is flexible. So.
Not like that. See, if I tell you integer, is it static or dynamic?
Static.
It's a static.
Inside the module, it's a static.
The memory gets allocated at compile time itself. Allocated at compile time. Why is it static? Is, see, for an integer, the space is already fixed because it will require 32 bits. Integer based variables require 32 bits of space, so that no one can change the definition, right? That is a fundamental behavior of an integer, so that makes it static. If I declare byte b, is it static or dynamic?
Dynamic.
Sir. 8 bits are static given.
Static only, because
Again,
it's
it's a
again
static, no?
8 bit space. So like this, there will be few things that is static, and by seeing them itself you can tell it is static. Now if I tell you integer int array of this one, you will tell that it's a dynamic array. The name itself tells you that it's a dynamic. So as you start using language, within few weeks you will know what is a static construct, what is a dynamic construct. Okay, now in this context, let us learn a new concept called as different phases of data type uses. See, different phases of data type uses. Definition stage, instantiation, creation, and randomization. Okay, someone has asked a question. Let's address that question first. Okay, new 100, and when you do new 200 means memory will be increased or it will be delete previous locations. It will be like this: int a equal to new of 200. In the brackets, if I write int a, it will retain existing 100 locations of 100 location values of int array. If I give without this thing, it will create all 200 elements with default values. Means it will not retain, it doesn't retain existing values. So the difference is passing int a in the brackets here after new. If you pass it, whatever elements that are there already in int a, they will be restored, kept, and new elements will be, new 100 elements will be created. Only 100 elements will be created newly. Whereas if you completely do new of 200, it will increase, it will create all 200 elements with default values. I hope, Chetan, it's clear to you. Okay, next, if I go to different phases of data type uses: definition stage, instantiation, creation, and randomization. Definition means there can be two types: language provided definition or user defined data types. To understand this, let us take one example. Definition can be two types. One is language provided, one is user defined definition. What do we mean by language provided? What do we mean by user provided? Let's understand that. If you take integer a, in this case, integer data type, integer is a data type. Is this data type, is this integer data type language provided data type or user defined data type?
Language provided.
Language provided, right? Okay. In some cases, if you are familiar with C language, you will know that C language has a concept called as type def. which can be used to create user defined data type. I can declare bit 3 down to 0 or reg 3 down to 0 or whatever. Reg nibble. Nibble means 4-bit vector. Bit vector is what we nibble. This is an example of a nibble underscore t is an example of user defined data type. What is that making user defined data type is the concept of type def. So using nibble underscore t, I can declare a. Now this a represents a is a 4-bit vector. So this is an example of a language provided data type. This is an example of a user defined data type. That is the first concept. Next, what we have done here is called as instantiation. This is called as instantiation. You are instantiating integer as a. You are instantiating nibble underscore t as a. You mean not to confuse, I can declare it as b so that I can give different names here and different name here. Okay. Now, third stage is called as creation, where we allocate memory to a data variable. This is where the static data types and dynamic data type differs at the stage of creation. For static data type, this is not required. For static data type, this is not required because memory automatically gets allocated for them. If I declare int a, integer a, when I declare integer a, I don't need to do a equal to new is not required because 32-bit memory is already allocated to integer a. So since 32-bit memory is already allocated to a, we don't need to do new. So this is the case for all static data types. I mean, anywhere you see that data type is static in nature, we don't need to use new. If I write byte b,
Some question that
yeah,
compiler will give any issues.
sorry, please come again. No, compiler will give you the issues. If you do this, compiler will give you the issues.
Yeah.
Okay. Whereas, yeah, any other questions? If I declare integer int array of this one, this is a dynamic array, int a equal to new of 5. This is dynamic. So hence we are using new to allocate memory. So most of the times what you will see is wherever you are working with dynamic construct, we have to use the new constructor. This is called as a constructor. Why is it called as a constructor? It is allocating memory. By allocating memory, it is constructing the space. So that's why it's called as a constructor. How much memory to allocate? That is this one.
Is it mandatory to give this new? If we are not providing new, we can't do anything, right?
We can't work. I mean, for dynamic data types, in most of the cases, with some exceptions, we have to always use new. If you don't do that, that memory itself doesn't exist.
Okay, if you are not providing any location, just new only, it will allocate only one space. Or...
No, actually, in case of that concept will vary. See, the new gets used in different styles for different constructs, for different dynamic constructs. Okay. Ideally, I wanted to introduce these concepts later in the flow, but since you are asking this question, let me tell you how it works. If I have a class, Ethernet packet is a class, PKT. For a class, we have to use this kind of packets. I mean, we have to use normal these brackets. Okay. For a dynamic array, int dynamic array, we have to write square brackets and how much spaces to allocate. Let's say 200 elements I want to allocate. So like this, different constructs can have different ways of using the new. As of now, let's not get deep into it. Just right now, remember that new means we are allocating the memory. Now, how much memory to allocate, where to give the number, where not to give the number, here no need of giving number actually. That is not required at all. All those things we'll discuss as we go forward. But one thing you need to remember is, if I without doing new, we can't use int dynamic array. It's not possible. It won't allow it because that memory itself doesn't exist. You can't do anything. Where the memory doesn't exist, you can't store anything. You can't access that memory. So hence, you always have to do new when you work with dynamic data types.
Thank you.
Next, that is creation. Then comes the concept of randomization. Okay. Did I explain that in the next slide? Let me see. No, I haven't explained. Let me explain that. Okay. Let's talk about the term randomization. What is the need for a randomization? Can someone tell me, for a verification engineer? For a verification engineer,
creating different stimulus.
Why randomization is important? Yeah, can you please come again?
For creating different stimulus means different values for a particular variable.
Yes, basically for applying various types of stimulus, we need to do randomization. Let's understand this through one simple example. Please give me 2 minutes. I'll be back. Then we'll continue with it. In the meantime, just please read this once. Okay, I'm sorry. So let us now talk about the randomization. Let's understand why randomization is important for verification purpose. If you take any electronic device, same electronic device gets used differently by different people, by the same people on different days. I mean, if different people they use it differently. And same electronic device, like say my laptop is there, I'm using today, I'm using it in one manner. Some applications are running. Same laptop, when I use it tomorrow, I'll be using it in a different manner. So the kind of inputs we apply to the design, to the devices, are random in nature. Today I am using in one manner, tomorrow I'll be using in different manner. So the different inputs are getting applied. So how do you get the similar behavior? How to get similar behavior during the verification? During the verification of the design. So that is called as randomization. By means of randomization, we can generate that kind of random patterns, which will give you a behavior which is close to real life uses. In real life, how we are going to apply different kinds of inputs, the similar kind of behavior you'll get by means of randomization. So how randomization happens? In Verilog, we use $random, or at best you can use $urandom range for randomization purpose. To give a range, within a range you want to randomize, you can use. In fact, this is more belongs to system Verilog only. As per me, it's more of system Verilog only, but I'm including with Verilog also. Whereas if you go to system Verilog anyway has this $random and $urandom range is there. Other than that, there will be some powerful concepts like rand case, randomize method will be there. These things make randomization quite easy in system Verilog. Here you can only randomize integer kind of variables using these things, integer based variables. Using this, you can do the randomization of a class object. So as we go forward, you'll see that this concept of rand case and randomize will be very important, and they'll make the overall concept of test case development a lot easier. Now that is about different phases of data type usage. Let us now go to the next concept, that is constructs and pre-implemented methods. Verilog doesn't have any pre-implemented methods except system tasks. If you take Verilog, everything you need to implement from scratch except for system tasks like $display, $monitor, $read memh, write memh, except for those things, everything need to be implemented. Verilog doesn't have pre-implemented methods. Whereas if you take system Verilog, no pre-implemented methods in Verilog. Whereas if I take the same thing in system Verilog, every construct has a lot of pre-implemented methods. What does it mean? If I take one construct called as mailbox, there is a construct called as mailbox in system Verilog. Mailbox, I told you, right, similar to FIFO. If you do FIFO in Verilog, if you think of FIFO in Verilog, we have to develop it from scratch. You have to write module FIFO, ports, end module, then you have to implement the functionality. This whole thing need to be done from scratch. In Verilog, we need to do from scratch. In system Verilog, we don't need to do that. In system Verilog, then once you have developed the FIFO code around 100 lines of code, 100 or whatever lines of code, we need to then use FIFO instantiation as U1 port connection. This all you have to do. This is how it works in Verilog. In system Verilog, we can avoid this. We don't need to do that. All you have to do is directly the mailbox is available. Mbox equal to new of. So you are creating a mailbox. Now here you use a parameter depth equal to 16. If you want to override the parameter, what will you do? Hash dot depth 32. Let's say you want to give a depth of 32 or depth of 100. This is how you will do it. How do you give depth here? 100. That's it. Here you are doing the parameter overriding to give the depth. In mailbox, to give the same depth, we have to use the concept of new of 100. So a mailbox with size of 100 gets allocated or gets created. So if you compare this piece of code and this piece of code, which one is easy to work with? Can you tell me, the first one or second one?
Second one, sir.
Second one is much easier, right? Can you tell me why? What is that makes it easy to work with? What is that is making it easy to work with?
You told that about pre-implemented functions we have in system Verilog, but in Verilog we do not have. We need to build everything from the scratch.
Yeah, basically in Verilog you have to code everything from scratch. All the methods, everything need to be coded from scratch. Whereas in system Verilog, this is already implemented inside the language already. Now you may say there is no FIFO in Verilog, right? In system Verilog, the similar concept is mailbox. It's like the same thing comes as a different name. Now when you want to work with the in here, if you want to work, how do you use it? Actually, it's very complex, right? In Verilog, how do you do? You have to drive at the rate of positive edge of clock. You have to do the connections. Then you have to drive write data equal to some data dollar random, write enable equal to 1. All these things you have to do. So on, right? This is what we have to do. In system Verilog, that much effort is not required. All you have to do is mbox.put whatever data you want to put. Let's say you want to put 15 into the mailbox. Mbox.put 37. So how many elements have I put here? Can you tell me?
One element, because 15 or 37, one element is put.
2 elements have been put into the mailbox.
Yeah.
2 elements we have put into the mailbox. The same thing would have been lot difficult with FIFO. So at every stage, the coding becomes simple when you work with system Verilog. See here, you have to again define the FIFO. You have to instantiate by doing all the port connections. Then even using the FIFO is complex. Here, instantiate, you don't need to define mailbox. You directly need to instantiate mailbox. So now tell me, mailbox is a user-defined data type or language-provided data type?
Language provided.
Language provided.
It's a language-provided data type. So, and by using new, you are allocating the memory. This is called as instantiation. This is called as creation, where you are allocating the memory. And this is where you are using it. You may tell, why are we not randomizing it? See here, there is no need to randomize it actually. See, mailbox is a element where randomization is not required. Let us take one example to understand how to work with mailbox. So the whole benefit of mailbox comes because of pre-implementation and the methods which are already provided by the language. See, it comes with the methods like new, put, get, try put, try get, delete, peek. All these methods makes working with Mailbox lot easy. So user don't need to implement put method, don't need to know how get method is implemented, don't need to know how to implement try put and try get. User only needs to know how to use the Mailbox methods. That's all. So someone is asking, this Mailbox can be used in design also. No, it cannot be used. Mailbox is non-synthesizable. That means it is only for test bench development purpose. Okay. SV can be used. Okay. SV can be used for design. Yes. SV can be SV. System Verilog has constructs which are for design purpose, RTL coding purpose, and System Verilog has other set of constructs which are for test bench development purpose only. Test bench development purpose only. For example, object-oriented programming, dynamic arrays, associative arrays, queue. These are all for test bench development only. They are not suitable for design coding purpose. Yeah. Any questions?
In this System Verilog course, will we learn the construct used for design, System Verilog construct for design purpose? Will we use it, or
Very
only
minimal, very minimal. We will be mostly focused on test bench development activity. I mean,
okay.
There isn't actually a lot of changes. See, for example, always in Verilog becomes always underscore form, always underscore flip flop, always underscore latch kind of logic in System Verilog. Like that, there are minimal updates are there. Not like they have added hundreds of constructs. They have done few construct addition. Those things will be discussed.
Okay, so Verilog will be on top of that. These constructs we need to learn to design using
Yes.
System Verilog.
See, whatever is there in Verilog is always there in System Verilog.
Okay, sir.
We are going to additionally learn the things that are added newly in System Verilog. Okay. Next. So we were discussing the example of a mailbox. Let me tell you, my idea is create a FIFO kind of structure in System Verilog. FIFO behavior in System Verilog. It is as simple as module TB, module test bench. All you have to do is just declare mailbox. You call it as XYZ, anything you want to give, mbox equal to new. How much space you want to give? Let's say 16, depth of 16. That's all. Initial, begin, end. You want to put 5 elements into the mailbox. Mbox dot put. Let's say 10, 20, 30, 40, 50. You have put 5 elements. Put 5 elements into the mailbox. Now get 5 elements from the mailbox. So mbox dot get. Let's say a. You want to get it as integer a. Since you have put integer, you declare integer a. You are getting it as integer a. How many times you are getting? 5 times you are getting. So repeat 5 times. 5 times I'm getting, so I have to repeat 5 times that activity. Then do $display. A equal to %0d a. Tell me what will be the first value of a printed? Can you tell me?
10.
Right. So since I'm changing it, I'm compiling a new file, I'm writing mbox. And since I'm compiling it, I'm giving tb. Run -all, rest everything is same. So go here, just do run.do. See, values are coming as 10, 20, 30, 40, 50. Now imagine doing a similar behavior in Verilog. I want to create a similar behavior using a FIFO in Verilog. It will be very difficult. I mean, what is that makes it difficult is you can't directly do it. You have to declare module FIFO, end module. Then you have to instantiate FIFO. Then you can't directly call put method. There will be a lot of challenges here. So that whole thing you don't have to go through when you work in system. Is mailbox just like a queue? Let's take one question. It is similar to queue. Mailbox is similar to FIFO. See, queue can do many things, right? Queue, many things are possible. Means you can push, you can get push in the push front, push back, pop front, pop back. There are many such possibilities. Insert is possible. Shuffling is possible. There are many things are possible. Shuffling is possible. Reversing is possible. All those things you can't do with mailbox. That means, what does it mean? Mailbox behavior is a subset of queue behavior. So we can't say just like. It's a subset of queue. That statement will be correct. I hope it is clear. Any other questions?
No, sir.
So I hope you understood the concept of construct and pre-implemented method. Like that, you take any construct in system Verilog queue. It comes with methods like push back, push front, pop back, pop front, shuffle, reverse, delete, and insert. Means whatever you want to do with the queue. Like what will you want to do with the queue? Push the elements in at the back of the queue. Push the elements at the front of the queue. Pop the elements from the back of the queue. Pop the elements at the front of the queue. Shuffle the elements of the queue. Completely shuffle them. Reverse the elements. Delete the elements. Or insert elements into the middle of the queue. That all things, these methods come with the queue. In Verilog, all this needs to be implemented by the user. In system Verilog, we don't need to implement any of that. They all come with the language. You just need to know how to use pushback, how to use push front, how to use pop back, how to use those methods, how to call those methods. That is what you need to learn. What do we mean by how to use? Which argument to pass? Let's say if I have declared a queue, int queue $. Dollar is what tells that it's a queue. How to use queue? Int queue push back 10. Okay, let's say int queue pop front a. This is wrong. This line is wrong uses. What is correct uses then? I have to write a equal to pop front. This is correct uses. So you should learn which style of usage is correct, which style of usage is wrong, and what is that function is about. Those things you need to learn. In Verilog, you need to worry about how to implement that method also. So like that, for every construct you take dynamic array, it comes with methods like new, num, delete. Class comes with methods like new, randomize, pre-randomize, post-randomize. The important thing here is knowing how to use these methods and how the prototype looks like. So I told you, right, how to use pop front, how to use pushback, how to use insert. Let's say if I tell you insert, int q dot insert 10, it is wrong. Why it's wrong? Can you tell me? what do you think is the wrong by going by this number, this usage? What do you feel that there is wrong here?
Sir, we need to give two arguments here at insert position and the value to be inserted. There is only one argument is there.
So basically, the logically, you will see that we should be giving two arguments, right? Okay, so right now we are only telling you what value to insert. So that will make it, let's say, insert 3, 10. That means at 3 index correct uses. So at 3 index insert 10. So this is what you should learn. That okay, see, anyone can just write like this, but that is wrong, right? You should know what does this do, what arguments to pass, in what order to pass. Let's say someone passes 10, 3. Does it make it correct?
It's correct, sir. At 10th location,
Number wise it's correct. Number wise it's correct, but if I wanted to do this, then it's wrong. Okay, so that is what I mean by you should know prototypes, how to use these methods and how the prototype looks. Okay. Next, so we will just discuss this and stop the session. If I write module top int a of 10, it is static data type because it's a static array. Verilog only supports this. I mean, here you can't increase the size, you can't decrease the size. Here it is dynamic data type, and we have already discussed about what is static and what is dynamic data type, the concept of new, everything we have already discussed. We will stop the session here. In the next session, wait, I think let me just conclude with this slide because this will kind of end this topic altogether. I have already explained you, right, the concept of how to use new and how we can decrease the size and we can increase the size by using the concept of new. We have already discussed. Then I have already told you about pre-implemented methods that you can declare directly a mailbox based data types and you can put the elements into the mailbox. You can get the elements from the mailbox and you can display, and you can use various mailbox methods. For example, I wanted to get the how many elements are there in the mailbox, how many elements in mailbox, how to get it. So there is a method called as mbox.num, will tell you how many mailbox elements are there. Now the question comes, how to use this method? It's simple, right? How to use this method? So I have to write count equal to. So this is what you need to learn. See, someone if passes count here, then that will be wrong. Count will be a return value. Now you do $display count equal to %0d count, and let's run this. Undefined variable count. Count is 5, right? Because 5 elements were there. Now you may ask, how do I remember so many things? Just remember one guideline. One common guideline is that if that method is if method is a function, then it will return argument, return of function. If method is a task, then it will be return of task argument, task output argument. What it means? See, in this case, get is a task, so a will come as a output argument. Num is a function. Num is a function, so it will be a return value of the function. So that basic concept, if you remember, even that becomes easy for you to work with. So the same thing I have shown here. So with this, we will stop with the topic of pre-implemented methods. So in the next session when we meet, we'll continue with system Verilog language concepts, and further we'll get into the basic language constructs of system Verilog. So we will stop the session here. Any questions?